Good afternoon. My name is Steve Boggs. I'm the chair of the physics department here at Berkeley. It is a great honor to introduce this year's distinguished Emilio Segre lecture. Dr. Raymond and Beverly Sackler generously endowed this lecture in 1987, and it has been an annual tradition in our department ever since. This lecture honors the experimental work of Segre, as well as the invited lecturer. Emilio Segre was one of our most esteemed faculty members in the physics department. Together with Owen Chamberlain, he won the Nobel Prize in 1959 for the discovery of the antiproton. He had been a student of Enrico Fermi's in the late 20s, and later a professor in Palermo. While Segre was on a visit to California, Mussolini passed a law barring Jews from university positions. Segre was unable to return to his home country. However, Italy's tragic loss was America's gain. He became a group leader for the Manhattan Project at Los Alamos National Laboratory, and eventually a professor at Berkeley in 1946. It is always a special pleasure when we have a chance to honor one of our alumni. Today is one of those occasions. While we never miss an opportunity to boast about the 9 physics Nobel laureates among our faculty, did I mention 9 Nobel laureates among our faculty? We are also extremely proud of the additional 7 Nobel laureates among our alumni, including today's speaker. David Wineland will present this year's Segre lecture entitled Superposition, Entanglement, and Raising Schrodinger's Cat. David is a professor of atomic physics at the University of Colorado at Boulder and a research scientist at NIST, the National Institute for Standards and Technology. David shared the Nobel Prize in Physics in 2012 with Serge Haroche. The citation reads, for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. As you may know, in the paradoxical world of quantum physics, the same object may exist in different states simultaneously. Thus, Schrödinger's famous thought experiment, which was actually intended as a critique of the Copenhagen interpretation of quantum mechanics. Can a cat in a closed box be both dead and alive at the same time? Wineland has developed ingenious experiments that study quantum phenomena when matter and light interact, and he has successfully captured electrically charged atoms or ions in a trap, a kind of trap, and studied them with the help of small packets of light, or photons. Wineland has been able to create incredibly precise clocks based on this research, and discoveries such as these will result in the building of computers that are much faster than those that we use today. David was born in Milwaukee, Wisconsin, but graduated from high school in Sacramento. He spent his last 2 undergraduate years here at Berkeley, majored in physics, and graduated in 1965. He got his PhD at Harvard in 1970, and he did his postdoctoral work at the University of Washington. In 1975, he joined NIST, which was then called the National Bureau of Standards, and started the Ion Storage Group. David is a fellow of the American Physical Society, the American Optical Society, the National Academy of Sciences. He has also been awarded the Einstein Prize for Laser Science, the Arthur Schawlow Prize in Laser Science, the National Medal of Science, the Benjamin Franklin Medal, and of course, the Nobel Prize in Physics, just to name a few. I literally ran out of breath reading those awards. Today, we are very fortunate to have Professor Wineland here to present this year's Segre lecture and help me in welcoming David back to his alma mater. Welcome, David.
Well, thank you, Steve. It is a pleasure to be back. I must say I'm still nostalgic about Berkeley. I really liked my couple of years here, so it's really nice to return. So I guess, of course, not surprisingly, probably the reason I was invited here was because of the Nobel Prize. And I know there's a lot of, I could give a highly technical talk on what's going on, but I know a lot of people are here just to get a general idea of what's going on in this area. So I have to apologize to my physics colleagues. They're not going to probably learn too much physics here, but anyway, this was a fun talk to give. So I think one thing I should say at the outset, I think, both the fellow I shared with, Serge Roche, and we both feel that, obviously this was a great honor, but I think without doubt, there's so many people that we work with and do the similar work with around the world that I think we're more representative of the field than, because there's so many people doing such good work that other people, it could have been other people besides myself for sure. So what I'm going to do is first introduce this idea of Schrodinger's cat that maybe not everybody's familiar with, but what always amazes me is that Schrödinger, one of the inventors of quantum mechanics, had the courage to express his dissatisfaction with the theory. And as amazingly successful as it's been, if you take it literally, it leads to some strange consequences. And that is, so he posed his dissatisfaction with the theory with this example. So what you want to think about, suppose at least the way he posed this problem was, suppose we have a cat and inside of a sealed box so that we don't interrupt it from the outside. And there's a single radioactive particle, and then there's some mechanism such that if the particle decays, that releases poison and the cat is dead. And although it would be impractical to do this, in principle we could write down the quantum mechanical equations that describe this situation. And before we look in the box, all that quantum mechanics tells us is that the cat exists in a superposition state where it's neither alive nor dead. It's both at the same time, which of course makes no sense in our everyday experience, but this is what quantum mechanics tells us. So here, what this notation is meant to represent is that it's simultaneously a situation where the particle is undecayed, the cat is alive, the particle has decayed, and the cat is dead. So for the non-physicist, I think an analogy to this that I think conveys a couple of the key ideas in quantum physics. And if we think about this look at this box up here, we can, if we let our eyes adjust in different ways, sometimes we'll see this face be in the front, as this image indicates, or perhaps this face in the front, as this one indicates. And I think this is a good analogy to superposition, because this image up here has both of these conditions, these states we would say in quantum terms, at the same time. It's neither one or the other. It's both at the same time. Another thing about this particular example that I'll come back to later, but it turns out that even though we can put quantum systems into these superposition states, when we measure it, it tends to collapse into one configuration or the other. So when you tend to see one image or the other, that's very much like quantum measurement. When we finally go in and measure, and if we look inside the box with a cat, it's going to be either dead or alive, not both. It's this collapse we say is very much like how your eyes tend to project onto one image or another. And just, I'm not going to say much about entanglement, but what the entanglement expresses is the correlation. So at least if you'll play along with me, if I tend to see this face in the foreground, then on this box I also tend to see the same face in the foreground, or the other case. And so this idea of entanglement is meant to express this correlation. In the case of Schrodinger's cat, it's where the cat being alive is correlated with the particle undecayed and vice versa. So anyway, so Schrödinger and others, struggled with this apparent problem, that quantum mechanics only by itself predicts superpositions, and somehow we have to inject this idea of measurement into how we use the theory. And so one way at that time, the experiments weren't advanced enough. It was even though the founding fathers, including Schrödinger, would kind of dream up these situations thinking about elementary particles, atoms, and so on, those kind of experiments couldn't be done. So anyway, in one of Schrödinger's papers in the early 50s, he said, well, maybe, I think, at least this is the way I read this, maybe we're leading ourselves astray. We can think of these situations in terms of small numbers of particles, but in fact, we can never do those kind of tests. And it leads to these, extrapolated to the macroscopic world, it leads to these ridiculous consequences, meaning the situation like Schrödinger's cat. But now, of course, we can play in this world. We can, at least with small systems, realize these situations that the founding fathers puzzled over. And so, in a way, it was just a matter of technology. These days, at least for small systems, we get enough control and isolation from the environment that we can actually make these superposition states and entangled superpositions for that matter. And so this is going to be my story. Now, one thing that was nice, the way the citation for the prize was awarded, it was the prize is often given for a particular discovery or some very specific thing, and it was worded in a fairly nebulous way. So in some ways, it covered my whole career. So you're going to get a short version of my career here. So when after leaving, graduating from Berkeley, I went to work I was a graduate student in Norman Ramsey's group at Harvard. And this was a time not very long after Norman Ramsey and his colleague Dan Kleppner had invented and demonstrated the hydrogen maser. A maser is just like a laser, only M stands for microwave, so at low frequency. The principles are very much the same. And this device, this hydrogen maser, was then and still is used as a very precise clock. It's an oscillator that has a very precise and well-controlled frequency. Anyway, so when I was there, Norman wanted to have all the hydrogen isotopes, high precision measurement on all the hydrogen isotopes. So this was the picture of the group at that time. This is Norman Ramsey here, and this is me trying to get close to the boss. Anyway, so my thesis was to make this deuterium maser and measure its hyperfine frequency. And I like to say I think I'm the only one in the universe that has this memorized because it was the main result of my thesis. But more importantly, what I think first of all, it got me hooked on these kinds of experiments where precise control and precision measurement were involved. And also, even at that time, we were dealing with superposition states. In this case, it was superpositions of the upper and lower energy state that the hydrogen maser worked on. And actually, they were, even by today's standards, fairly long-lived. While these atoms were inside this maser cavity that they were radiating to, they were in superposition states for on the order of a second. And then, so after my graduate work, I went to work at Hans Stehmelt's lab at the University of Washington. And the reason I was attracted to go there is Hans Stehmelt had been doing experiments, very high resolution spectroscopy experiments on ions, charged atoms rather than neutral atoms. And I was attracted to that for the same reason I was attracted to working in Norman Ramsey's lab. But about the time when I was transitioning to there, he was more interested in pushing another experiment he had, and that was to measure the magnetic moment of the electron. Any electron behaves in part, one of its features behaves like a little bar magnet. And the interesting part about this is that quantum mechanics can predict the strength of this magnet to about 12 decimal places these days, and it's basically, I think it's the most precise prediction of quantum theory in terms of ad hoc theory, in this case quantum electrodynamics, that there is. Anyway, so he was interested in that, and so what we did in those experiments is we had what we call a trap, and it's basically just an electrode structure. Since electrons are charged, we can grab onto their charge with electric fields. And what you can think of if this doesn't look so familiar, what you can think about if we have a group of electrons, it's just like marbles that can roll back and forth in a bowl. So that picture works just fine too. For the physicists and electrical engineer people out there, in fact, the electrons inside of this electrode structure look like a tuned circuit, and in fact, we can put this tuned circuit into a simple voltage divider circuit. Anyway, the basic message here is that we can excite these electrons back and forth in this atomic bowl, and the strength of their oscillation gives a current, which is then proportional to the number. And for this way, we could tell how many electrons we had in this experiment. Well, not long after I was there, it became clear that the highest precision in this magnetic moment measurement would come if we only had one electron in this trap. And I mean, one reason was just simply if the electrons bump into each other, they can perturb the measured frequency of this magnetic moment. So one of my main tasks while I was there was to be able to isolate single electrons. So what we did in the experiment is we would excite the motion. Again, you can think of the marbles in a bowl to such an extent that occasionally one of the marbles would fall out of the bowl. That would cause the current to go down. In the electrical picture, all we were doing is one of the electrons would occasionally strike one of the electrodes and be lost. And so we'd see this staircase kind of picture. And the interesting case, of course, is when we got down to this last step, then we'd stop and then do other experiments on single electrons. So this was a precursor to this magnetic moment measurement, and later led to a very precise measure, one of the first precise measurements, and actually Hans Stamos, in large, received the Nobel Prize for this experiment. Anyway, when I was there, we had some ideas about laser cooling. I was still thinking about spectroscopy clocks, and one of the so when I was there, Hans Stamos and we had some ideas about how to do cooling, and also simultaneously Ted Hench and Art Schellow had ideas. At that time, they didn't look so much the same, but in fact, they're basically the same physics. And I won't have time to say very much about laser cooling, but the central idea we used in these early experiments is that a laser, laser beam coming from this direction, we can tune the frequency of the laser such that an atom moving against the laser will scatter photons. And when the photons are scattered, each photon scattered imparts a momentum kick that retards the motion of the atom or the ion. And this basic idea then was this dissipation of the motion gave rise to the cooling. And the reason this was interesting, I mean, it was interesting by itself, but why it was interesting for atomic clocks was that it's one of the interesting things we have to take account of in our atomic clocks, and this is an effect that comes from Einstein's theory of relativity, which says that for a moving object, time runs at a different rate relative to a stationary observer, and for the conditions we typically have in these atomic clocks at room temperature, it's a very small effect, but nevertheless, it's one we have to compensate for or correct for in these high precision measurements, and so that was interesting potentially then for future atomic clock work. So when I went then after my postdoctoral position, I went to it was then called the National Bureau of Standards, and now it's called the National Institute of Standards and Technology. And at that time, well, my first job was to make the cesium atomic clock work. It was based on cesium beam, but the same idea as this hydrogen. The atoms can radiate at a certain frequency, in this case around, that's microwave frequency, around 9 gigahertz. And this device here, atoms would traverse through, and during their traversal, we would measure their oscillation frequency. Anyway, my first job was to help get that device running, but and also at that time, at least the time and frequency division of NBS, it was really, it didn't do any basic research. We had calibrations to do, and of course we had to provide the unit of time, the second, based on these oscillations in cesium. But fortunately, my boss at that time, Helmut Helwig, he had the vision that we were going to start research, and so I was really lucky. And he, after this, getting the clock calibrated, he was able to get some money where we could try this idea of laser cooling. And so one little side story was, I knew that my boss as a postdoc, Hans Stehmelt, he had gone to work with Peter Toshak, who was then in Heidelberg, to work on this laser cooling. And of course, we got started too, somewhat after that, working on this. And so I actually knew that they were working on it. I didn't know where they were. They actually didn't know about us. And but what's interesting about this, we both got results about the same time. And you'll notice, our paper was published a little bit before theirs. But to be fair, if you look at the submission date, theirs was received at the journal one day ahead of us. So you'd have to say they won the race. But anyway, it's an amazing near coincidence because we really didn't know, each of us didn't know where the other group was. But anyway, so in these experiments, the way that they were pretty crude by today's standards, but the way they saw this heating or this laser cooling was that they observed when the laser was tuned properly, they could hold the ions in their trap for a longer time than when it wasn't applied. In our case, we could benefit from the kinds of things that we did in the electron experiments. So we would look at the induced currents in the electrodes again. In this case, rather than it being a driven excitation of the motion, we just looked at the thermal noise of the electrons as they jiggled around due to their motion at room temperature. And what was nice about that is that this thermal noise induced was a direct measure of temperature. And so when we applied the laser, we could see it fairly clearly. It certainly wasn't the amount of cooling that we did then is not very interesting compared to what we can do today. But it allowed us to do some at least some simple checks of the idea. So this was our group in 1979, not very long after those experiments. So it was these four guys here, and I've actually one nice thing about for me, I've been at NIST is basically I worked my whole career with these guys, and the only thing that's embarrassing for me, if I put a more recent picture on my colleagues Wayne Itano and Jim Berquist, they look pretty much the same with these other guys. They didn't weather the years so well. So anyway, we're a much bigger group now, and we have two main projects. We work on atomic clocks, we always have, and we also work on quantum computing, and I'll say a few words about that, but it's certainly the progress is due to all these good students and postdocs and visitors. So one of the things, just as as for the electron experiments that Hans Stehmelt was doing, it turned out it was pretty clear that we could get the highest precision, that is the smallest errors in our measurement when we measured frequencies of oscillations in our ions if we went to one ion. For the similar reasons, the ions bump into each other, or they perturb the oscillation frequency and things like that. So one of the tasks we went after then was to try to get down to a single ion. In this case, clearly Peter Toshek's group beat us there, but anyway, we did very pretty similar experiments. In this case, we also could look, in this case, rather than the induced currents, we'd look at scattering from the ions, and as an ion was removed, the scattering would go down in steps. And then just as for the electrons, the interesting case was when we got down to 1. In this case, we removed ions through a simple charge exchange, kind of a chemical reaction process. So I'll give you an idea of how, just a basic idea of how these experiments work. So here, this picture is meant to represent this electrode structure that we apply electric fields to hold on to the charge of the ion. In this example here, this is a transition in the atoms where we, in this case, mercury, where the atom decays very quickly out of the excited state, and what that means is we can scatter a lot of photons, and this laser cooling process becomes then very, very efficient. So you can see this only lasts for a couple nanoseconds, and so we can scatter photons at that rate, and the ions very quickly cool down. And in fact, we could make pictures. One of the things that happens is that for most of the ions, they've had one electron removed. So these transitions that we excite, it takes much more energy simply because the attraction of the nucleus is stronger. So most of the transitions are in the ultraviolet. You can't see it with your eye. This is a picture with a video camera, but nevertheless, you can easily see with a video camera the single ion. I should have pointed out in the previous view graph. One of the nice things about these early experiments by Peter Toshek's group was that barium is one of the very few ions where you can actually see the scattered light. It's in the deep blue, but you can see it with your eyes. So with a small magnifier, you can actually see a single ion, a single atom with your eye. It kind of looks like a faint star. Anyway, so one of the, coming back to clocks briefly, mercury also has another transition, and this one the atoms stay up for a very long time in the excited state. And what it means is that when we apply radiation to the atom, it only absorbs radiation over a very narrow range of frequencies. And this is good for clocks because when we find that condition, when the radiation is absorbed maximally, then we can use that as a clock. We find that condition, and then we just count cycles of the oscillator, the laser in this case, that gives this condition of maximum excitation. And the way we detect is actually also very simple. What we do in these experiments is we start the atom down in this lower energy state. We apply this radiation for a little while. If the radiation is tuned at the wrong frequency, then the atom remains in this lower state. And then when we turn on this laser here, we can see the scattered light, and just as in the picture. On the other hand, when the radiation is tuned so that we promote the atoms up to this level, then when we turn on this laser, there's no scattered light because the atoms are residing in that level. And we can actually, it's used in a lot of atomic physics experiments, and you can see that what we did in this experiment, we collected light for roughly millisecond time bins, and this is just a longer time span. But what you can clearly see when the atom is in the lower state, we see the fluorescence, and when it's in the excited state, there's a little bit of background light here, but we can easily tell the difference between those conditions. So we have a way to detect essentially with 100% efficiency when the atom makes the transition. So I'll come back a little bit to this spectroscopy again, but one of the things that was interesting, again, in part for the clocks, we have this so-called time dilation shift that came from Einstein, and ideally to get to to suppress that to the highest degree, we want to freeze out the motion of the ion. Well, in the quantum world, we know that this sort of the energy of the ion, it can't exist in any given energy state, that is any given kinetic energy, it can only exist in certain discrete energy levels. So in the case of a harmonic oscillator, which the marble in the bowl is, there's a ladder of equally spaced energy states that describe the quantum motion of this atomic marble. And so what the interest was again, partly for just the interest in doing it, but also for clocks. The idea, the best case would be is if we could put it in the ground state of motion. It doesn't mean that the atom stops moving due to the laws of quantum mechanics. It kind of jiggles around, but there's a lowest possible energy level that it can be in. And so we set out after to do this kind of, to reach that ground state. And in these experiments, what we do is what you can realize is, or think about is that there's two kind of pictures that describe the situation. In the classical picture, the ion is moving back and forth in this bowl. And if a laser is coming from say the left side here, if you're sitting on the ion, what you see is the laser is frequency modulated. And so when we do this experiment, what this shows is data from the way I described before. When the atom when this laser that connects that transition is on resonance, then the fluorescence goes down because the ion is up there, the fluorescence from this laser. And we see these features, these sidebands, we say, and the one picture is it's due to these frequency modulation sidebands. In the quantum picture, what we can think of about this central feature, the one we're mainly interested in, it describes a case where we're exciting this transition, but the motion quantum number doesn't change. And since these are equally spaced levels, then it works for any of these levels. If we start there, we'd go to this level here and give rise to this feature here. In the quantum picture, these so-called sidebands, the upper one, when we're tuned to a higher frequency, it represents the case where the atom makes this transition of its internal states, but it also increases the motion quantum number by 1. And also the other side, we call it the red sideband, it represents a case where the transition goes, but we reduce the motion quantum number by 1. And this led to a kind of a natural way to do this cooling. And one other ingredient was needed, and it turned out we can arrange conditions, which is fairly common in these experiments, where after the atom is excited here, it'll eventually decay back down, but we can arrange conditions such that when it radiates back down, the motion quantum number remains the same. So similarly as before, if it's up here, it'll come back down to the same motion level. And so the way the cooling worked was pretty simple. We just, what we would do is tune to this feature over here. And so when the atom was excited, the motion quantum number would be reduced by 1. And then when it radiated back down, the motion quantum number wouldn't change, so we've lowered the energy by 1 quantum of motion. And so the experiment was actually very simple. We just leave the laser tuned to this frequency here, and eventually the atom, no matter what state it starts in, it walks down and ends up in this lowest state. And then the way we detect that is also very simple. And when it's down in this state here, then there's no energy level for it to go to here, so this excitation process stops. And what that means in this data is that this feature here, which we call the red sideband, disappears as the atom approaches the ground state of motion. And of course, we didn't do it perfectly in this experiment. You see a little bit of this feature left, and on the other hand, the upper feature still remains, and it's this ratio then allows us to determine that we were, at least on average, most of the time in the ground state in these experiments. So let me come back. I'll jump subjects in a little bit. Let me come back to another version of Schrödinger's cat. And so the experiment we did when we were able to do this cooling to the ground state, what we would do is I've changed notation on here to a more generic case where we just I'm just changing the labels, but you can think about this clock transition in Mercury if you like. But anyway, the idea is we start the atom in its motion ground state. We start it in its internal ground state. And then what we do is we can apply radiation where we first put the atom in a superposition of this ground and first excited state. And then this requires quite a bit of detail to explain, but it turns out we can apply laser forces on the atom such that it will excite the motion, but the motion, how the motion is excited depends on which internal state the atom is in. And so we could create a situation where at one instant of time, our atomic marble would be both on the left and the right side of the bowl at the same time, in this case correlated with which internal state it was in. And this is very much like Schrodinger's cat, we would say, because the more microscopic property, the radioactive particle was replaced by which quantum state the atom was in, and the more macroscopic property was this motion in the atomic bowl, which we would liken to be like Schrodinger's cat. And you say, well, it actually was really a small separation when we did this experiment. This represents, so we could only, in these early experiments, we could only separate the wave packet that describes the extent of the ion. It was about 10 nanometers wide, and the separation in this condition here was only about 80. So you might say, well, this is too small to be called a Schrodinger's cat. I mean, it is very small. One of the interesting things, though, is that you might say, well, if we could make our bowl big enough and separate the two parts of the wave function by 10 centimeters, that's much more macroscopic, and you might start to buy that's like Schrodinger's cat. But anyway, if you say this case is too small, then you have to say, where's the dividing line? Where does it stop being microscopic and become macroscopic? And so far, none of us can decide when this is true. So even though it's very small, some people, there was one letter to the editor after we did this experiment where we had referred to it as a Schrödinger kitten, and this letter to the editor says, well, that's still too big. Why don't you call it Schrödinger's fur ball? Anyway, but emphasizing this fact that it is small, but there's no way to make this dividing line. So let me say a little bit about this idea of quantum computing. So if we're going to carry this idea of superposition forward again. Now, with our again, I've changed notation on you here, but let's call the energy levels in the atom, we can label them now zeros and ones, just like the bits in a normal computer. And in fact, we can make a register of atomic ions, and we can put them in the 0 or 1 state to form a memory. But also, we can put the atoms in these superposition states where they're neither a 0 or a 1, they're both at the same time. So you can get at least an idea why this might be interesting, and that's how this quantum memory scales. So if we have, for example, if we had 3 bits in a normal computer, that would store one binary number, say, for example, 101. But in this quantum superposition sense, we can get these quantum bits to store all the numbers from 000 up to 111, all these possibilities at once. This is 8 possibilities, or 2 to the 3, and this is an example of exponential scaling. That is, as we scale up the number of quantum bits, the number of possibilities that are stored at the same time goes up exponentially. And kind of a popular example of this, if we had 300 bits in a classical computer, that might store a line of text. But in this superposition sense, it stores all these 2 to the n states at once. 2 to the 300 is about 10 to the 90th, and that's more elementary particles are in the universe. So basically, in this quantum superposition sense, it's fantastic, the memory. So this sounds pretty good, right? And then also, it turns out, I won't say much about quantum the way the operations work. But what's nice about this, when we plug in this superposition of all the numbers, the operations we do actually simultaneously operates on all these different memory elements at the same time. So there's this massive parallelism as well. Okay, well now there is a catch, and that if you come back to that box example, when we measure the state, just as for the box it would be one orientation to the other, with our quantum computer, when we measure this large superposition state, we're only going to get one, the register is only going to be one of these numbers. So we've collapsed this memory down from many possibilities down into one. And this is an important restriction. Now, in fact, though, that there are people now that have come up with algorithms that are willing or able to live within this restriction and do interesting things. One of the interesting side stories about this too is that these ideas were around starting with Richard Feynman in the early 80s, who suggested that maybe you could make a small quantum computer as a simulator. But what really got things going, a theorist, Peter Shor was his name, came up with an algorithm that showed if you could make this quantum computer, you could efficiently factorize large numbers. Meaning if you have a very large number that's a product of two smaller numbers, you can find the factors. And this is an exponentially hard problem with classical computers as the number of digits go up, but the quantum computer could efficiently solve this. So this sounds, for those that you don't know, it sounds like kind of a weird esoteric math problem, but basically why it was interesting is basically all the modern encryption we use. For example, when you buy something with your credit card or national secrets, they're encoded with an algorithm which would be compromised if we had this factoring machine. So naturally, the government was interested in this and has funded a lot of the research. I can only give an impression here. There's a lot of details, but one of the nice things is that the theorists rather quickly showed us that, in fact, we can make a so-called universal computer with just two operations, and it's true also with a normal classical computer. It may not be the most efficient way to make a computer, but in fact, all we need is a gate with a bit flip and, for example, an AND gate. It could be some other gates, but some non-trivial 2-bit gate. In a similar vein, in the quantum world, all we need to do is to be able to generate these superpositions, and that we've been able to do for many decades with radiation that we apply to these atoms, the internal states. But the harder part for everybody playing this game is to make logic gates. And this shows a logic gate here, which has this simple truth table. If the first bit is a 1, the second bit flips. And so actually we could do this classically as well, but the key part of this is we want this gate to work on superposition states as well, and that's where the difficulty and the power comes in. I'm just going to try to give you a flavor of this Shor's algorithm, but basically if we use those two types of gates, what we would do to factorize a large number is we'd make a superposition state that had a large enough register that it would include the number we're trying to factor, and of course the factors of that larger number. And then the algorithm, in very simplistic terms, is all we need to do is apply a series of two qubit gates and these things we called rotations, analogous to bit flips. And then the algorithm was such that at the end of performing this algorithm, there'd still be a large number of states this quantum register would be in. But when we do the measurement, this algorithm that Peter Shor came up with said you could take whatever number was measured, and you could use that in a classical number theory algorithm to determine the factors. But anyway, for the physicists out there, it in some ways it's kind of like a giant interference experiment where you're taking all these amplitudes that come in, and you're interfering in them in such a way that you can knock the number of possibilities down to a much smaller number, and then use the measured number to realize the factors. So let me just say a little bit about give a flavor of how this might be done with our atomic ions. And this was an idea there's two fellows, Ignacio Serac and Peter Zoller, who are well known among quantum optics people, atomic physics people. Anyway, they heard about this idea, and within 6 months they knew about our experiments, and they came up with an idea how this might be done. So what you can think about, this is meant to represent electrodes, kind of our atomic bowl again. In this case, we make the bowl fairly shallow along this horizontal directions, and it's fairly stiff in the other direction. So in the atoms, in our case the ions, when they go into this bowl and we cool them down, they all want to fall to the bottom of the bowl, but the Coulomb repulsion holds them apart into this linear array. So that was one ingredient they needed. So here's our quantum bits. I've gone back to this notation here where they can exist in superposition states. But then the key part of their proposal was that in some sense it's like a molecule. It has modes of vibration. In general, these modes of vibration are at different frequencies, so we can spectrally isolate these modes. And their idea in the simplest form was, okay, well, you start your register out you freeze out the motion, so all these modes are in the ground state. You take one of the modes, and the simplest one to think about is, say, where all 5 of these ions are oscillating back and forth in this external potential. And you just label the ground state 0 and the first excited state of this motion 1. And the interesting part, this forms a qubit, a quantum bit, but the interesting part about this is it's shared amongst all the ions. So in this classical picture of the ions oscillating back and forth, it acts like a data bus. All the ions see this quantum bit. And so their idea was the following, and it was that if we could somehow, before an operation, say a quantum gate, the internal states would be in some complicated entangled superposition, but we'd start the atoms out in the ground state of motion. Then their idea was we apply a laser beam such that we map this superposition onto this motion superposition. And then because that motion is felt by all the ions, is shared by all the ions, then if we could somehow make a gate between the internal degrees of freedom, noted the spin here, and this quantum bit of the motion, then we've basically done a quantum gate between the two ions because of this mapping procedure. And so I'll give you an idea, going back to this same picture we had for the laser cooling. I'll give you an idea. It's not a complete picture, but it gives the essential ideas of how this logic might work. And so let's suppose we start the atom. We've put the atoms in the ground state, and this is to represent the first bit. So both in the excited and ground state of the internal state, the atom feels this motion ground state. And then all we do is we, again, tune a laser to this red sideband. And what that does for a certain amount of time, and it transfers this amplitude all the way down into this. And so it's transferred this superposition of the internal states onto the motion state superposition. And then to get an idea of the logic, this kind of gives at least the flavor of how this works. So let's suppose now we've done that mapping, and in general, this second qubit, it's in internal state superposition, but also feels this motion state superposition. And the idea of the logic is, let's suppose we call the motion state quantum bit the control bit, and we're interested in doing logic on the internal state qubit. And the basic idea is we want to realize this truth table down here. So if the ion is in this first excited state of motion, then we adjust the laser so it completely transfers this population up here. In other words, we do the bit flip if the motion is in the 1 state. On the other hand, if the motion is in the 0 state, when we tune So that's that first case. And if, on the other hand, if the motion is in this control bit is in the zero state, the motion is in the ground state, then there's no place for this to go. So the internal state bit doesn't change. Now, as I said, this is a bit of a cheat here, but the key part is what we rely on. It's this conditional dynamics that's expressed in this simple example. So one of my colleagues, Chris Monroe, was first a postdoc with us and then a permanent member. He now has his group at the University of Maryland. But we were lucky. We had been thinking about some of these ideas in connection more with our clocks, but we were able to jump on this idea of Ignacio Serac and Peter Zoller, and we could do a demonstration fairly quickly after that. So if you walk in our labs, I won't impress any atomic physicists in the building here, but it's just dominated by lasers. So what we would call our quantum computer occupies a couple millimeter volume, and then everything else is lasers and trying to make the lasers behave we want. So that's what you would see in these kind of labs. One thing we do, it turns out that if we have other conditions, these voltages we apply to the electrodes, if we held everything constant, then the speed of operations sort of scale as 1 over the dimensions squared. So we'd like to, and the message here is we'd like to make these things small. So it's hard to make these using conventional techniques as we get smaller. So we've gone to lithographic techniques. And the picture that I showed in the first introductory slide with the title, it showed this picture here where, in this case, we take advantage of some of the capabilities in microelectronics where we can put the electrodes. The electrodes, rather than being a 3D structure, as this image shows, that they were all in a plane, and the ions would be suspended above this plane of electrodes. So each one of these tiny electrodes, squares there, can hold 1 or more ions or ion qubits and move them around and perform gates. And so this is the kind of, this is one way. We and other groups are thinking about how to scale this up. And this work goes on in a lot of labs, including Hartmut Hefner's group here at Berkeley that we're doing a lot of similar experiments with. So to give you an idea of the scale of this quantum computing business right now, what I've done here is list the groups that I know about that are just using atomic ions to pursue these ideas. And you can see it's a very big enterprise by now. But there's also a whole host of other possible quantum bits, neutral atoms, and also another popular one that's turning out to be very successful is quantum bits based on superconducting Josephson junctions that also have be configured so that they have 2 levels which can represent the quantum bits. So there's a huge amount of work going on in this area. Okay, so this is for the physicists. I'll apologize to the non-physicists here. But one of the interesting things is it comes back to this idea that Feynman had. If we can do more and better, the better part means we have errors in these systems, and we think it's just, we think we can beat it down by improving the technology, but that's the real name of the game, of course. Now anyway, this is an example of one of the. It turns out that the quantum gates we do represent. They behave just like spin-spin interactions, and these spin-spin interactions we can simulate. And what's interesting there is it might be a model for. It might be a system that we can then simulate condensed matter systems, the interactions of electrons, for example, in condensed matter. But what we'd like, of course, is a more general quantum computer, even if it's not a real accurate one. This might be useful in these simulation problem. And Rainer Blott's group in Innsbruck has done the most on this. He has the highest, or the gates with the lowest error rates, and he's done a lot on this. Now I haven't mentioned, but we've used some of these ideas of quantum logic in our spectroscopy experiments. I won't have time to talk about that. There's still the factoring machine, which which is by far the hardest problem anybody's thought of, but that's in some sense what still keeps us going. But like most new areas in science, I think more typically the applications that may really emerge in the longer term, probably nobody's thought of yet. I want to come back to this, if I think about, just come back to this Shor's algorithm. One thing I wanted to say is, coming back to Schrodinger's cat, is that at some intermediate time in all these operations we apply, we could say select out one of the bits, and so this would be the quantum state that we have. And all I want to do is, what I want to do with this example is this: in a large quantum computer, these other bits besides the 0th bit would represent a state where it's macroscopically different. I mean, if, for example, one case would be where where this part of the wave function is all in the 1 state and this is all in the 0 state, and this would represent a macroscopic difference in the magnetization that these spins of the ions have. So this really, if we can make the quantum computer, we are really making a much closer analogy to Schrodinger's cat because of the macroscopic size of the number of bits here. So let me just, I want to conclude by saying, not surprisingly, this is an effort of many people, and I mentioned my first 4 collaborators. We worked together our whole careers. We've been joined, John Bollinger joined us not long after that picture was taken. I mentioned Chris Monroe. We've been joined by some other guys here, and more, certainly also extremely important was the number of, good students and postdocs and visitors we've had in our group over there. I've been lucky that NIST has given us great institutional support, and I list some of my bosses here, and also I'd like to point out Catherine Gebbe. She's my boss's boss, so she was the physics laboratory director for 20 years, and one measure of her success is that after Bill Phillips and Eric Cornell and Jan Hall, I'm the 4th person to receive the prize under her while she's been director of the lab. Of course, obviously can't forget our funding agencies has been important for this work as well. Let me just say a little bit about the awards. Actually, I know Sol Puttermutter won the Nobel Prize a year before I did, so many of you have probably seen similar things about the ceremonies. So the prize is announced in early October. The award ceremonies are in early December. This shows a picture of Stockholm before the awards, and I must say the Swedes have a really nice way of celebrating Christmas. Very quaint but nice. They have these marketplaces, and it is cold there. It's pretty far north. In fact, this picture here was taken at about 3:15 in the afternoon, so you get the idea. But it's a wonderful. It's just a wonderful environment there around Christmas time. And unfortunately, they keep the laureates really busy. So I think I got 2 hours out of 12 days to walk down to the square. They were doing interviews and things like that. But nevertheless, it was really a charming place. This shows this was the main awards ceremony, and so this is this first row of people. These were the 9 laureates in 2012. There were 9 of us in the different fields. This is the royal family, and this is the king here who presents the awards to us individually, and it was extremely fancy. This is one of these things I'll never experience again, but it certainly was a wonderful experience. They treated us extremely well. Anyway, after the awards ceremony that night, then the king and queen invited a few people over for dinner. So one of the things that you quickly become aware of is that, unfortunately, each laureate, we're only allowed at these fancy functions. We could only invite 12 guests, and so the bad part about that is I had family there, and but I also wanted to invite my closest colleagues, and it's embarrassing because you can't invite everybody you want to. even as nice as it was. Anyway, the laureates and some of their guests were at this long table, and so 12 people times 9, that's around 100, right? This is 1,200 people, and what you quickly learn is that this is also a very big deal for Swedish societies and government officials, and so it is apparently it's the big event certainly in Stockholm. But nevertheless, it really was a wonderful experience. To give you an idea, this was the dinner tables, and they had all the serving of the meals was carefully orchestrated. I think there was only, I've forgotten the number, maybe 4 or 5 people for each one of these waiters, and so there's this huge cast of waiters, and they were, one of these guys up here, I forget which one, was actually the conductor, and it was just like a symphony, and everybody moved on time. It was very elaborate. So the last thing I want to say is that this is a picture of Serge Rocha, the fellow I shared with, and what was especially nice for me, I've known Serge's physics for almost all of my career, and I got to know him personally about 25 years ago, and in the meantime our wives also became friends, so it was certainly a particular pleasure for me because we have become good friends over the years, and so it was very nice to be able to share with him. Anyway, thanks.
Okay, we have time for questions. I'm going to bring the microphone around, so please wait until you get the microphone before you ask your question. Maybe I can start off with the first question. You gave a very precise precision physics picture of experiment to experiment to experiment, but has there been anything you've ever found in your career which just completely blew your mind away?
Oh, I don't know. I think I wouldn't say that, because we were actually in most of these experiments we were only realizing some of these things that Schrödinger and Einstein and others in the early days were imagining, and it was each one. It was fun to realize a number of these simple concepts.
Yeah, could you talk for a minute about what an observation is? Often in the Schrödinger equation kind of experiment, we want to think of an observer like a human being, and often I think of it as just the object giving up its energy to something else. So could you comment on that, please?
Well, this is a very interesting question, and I can't give a good answer to these ideas. I think one thing that I think there's a very interesting issue, and it comes back to the thing that bothered Schrödinger. All quantum mechanics predicts are these continuous evolutions where, for example, the cat is dead and alive. And so when you think about when we kind of have to avert our eyes to this measurement issue, because when we know we go in the lab and we can, just as with the mercury ion example, we either see scattered light or we don't see scattered light, which indicates which states it's collapsed into. But the weird part is about, our measurement apparatus and us, we're also quantum systems, right? So where does collapse come in? There's no logical place to put it in. And this is where these ideas of multiple universes come in. And, what I always found interesting, I went to a very interesting meeting a couple of years ago where there were cosmologists and quantum gravity people that I normally don't eat lunch with, but anyway, some of these guys had no problem talking about the wave function of the universe. So take your pick. I think it's something interesting. There's something to be resolved, but I don't, I can't tell you which direction to go to try to figure this out.
In your opinion, what do you think the best bet for the qubits of like the next quantum computers is? I know there's like 9 that people are working on or so.
Well, I think there's, I don't know, I think there's certainly a strong history of success with condensed matter systems. So that might be your gut reaction as to that's the way it's going to be, and that may be the case. Now, the one thing that's different though is that a classical computer, it relies on dissipation. We call it decoherence, to hold an atom, or rather a bit, to be a 0 or 1. That relies heavily on dissipation, and in this system, you want to completely get rid of dissipation. So the ground rules have changed so much that it's not obvious it will be a condensed matter system. At this point, I don't think anybody knows, and it's way too early to predict a winner.
Okay, here we go.
You just said it's early, but would you be able to comment on what schemes for scalability there might be for once you have a qubit? How do you make multiple ones?
Well, I kind of gave you briefly an idea how we would do it with ions, and with people working on one of the most successful condensed matter systems use Josephson junction, and the groups are now wiring them up. It's only still handfuls of qubits, but there's I think it's going to happen, and so we're slowly working up to these larger systems, but which one is going to be the right one? I don't think anybody knows.
There's a commercial company that's selling quantum computers called D-Wave. Do you have any comments about it? Have you heard about it? Do you know anything about it? Is it different than what you've been talking about?
Being a government employee, I have to be a little careful, but one thing you can certainly say, there was a lot of money put into advertising there. And so to be a little more serious, I think there was a lot of hype about that thing, and I think people are still trying to figure out exactly how it works. And it may end up doing something useful, but I think word is still out on that. So.
I'm not sure what the probability is of getting all of our questions from this half of the room, so I'm looking over here. Any questions? No? Okay, you guys are out.
David, I'm curious, if you average over your career, which fraction of the research projects that you started resulted in success?
Certainly on the first try, about 0.001%. And I think it is true. What I tell students that I think. And it's actually what motivates me. As experimentalists, we can conceive of some experiment, as we go along, and it rarely ever works on the first time. And so I think, some just take a lot longer, and we've had a few dead ends, but for the most of it, it does take perseverance. And the one thing though I like, and when I talk to students, I try to advise them that I think you have to like the process, and a big part of that is problem solving and doing the detective work to figure out why the experiments aren't working, and I always like that, and I still like that. But you certainly can't go in with idea of winning awards. You have to like the process.
I'm in the back with the cool students now, so any questions from the students?
Hi, I wonder to what extent are the atomic clocks you've created used today, and what are the possible applications of the higher precision?
Yeah, good question. So we're now, we've made some accurate iron clocks, and people working with neutral atoms have also made accurate clocks. And we're now down to a level where the error is down to about 1 part in 10 to the 17. So that fraction is where the errors are. And this is for clocks in the lab, so we can't make them, we're trying to make them portable, but that'll take a while. But so, one example always for clocks, their primary application for many centuries has been in navigation. And that continues. We all nowadays take, GPS for granted almost, that, and you might ask, well, we can certainly get to the supermarket no problem now with GPS, and so why do we really need anything more? And one answer is, this is starting to emerge. If we can do, say, navigation down to centimeter or millimeter precisions, one thing geologists are thinking about is that as a precursor to earthquakes is to measure earth strain, where the surface of the earth moves relative to each other at different positions. And so that, I think we're all hopeful that as we improve further the precision of the clocks, we'll get into those applications. And it certainly has been true that, even though people ask the question, well, haven't you done good enough? Why don't you move on to something else? That whenever we've made a better clock, there's always been an application. And that's been true for centuries.
I've found your lecture very interesting. I would like to give it a lot more thought, and I was wondering if you had a good reference that would approximate what you said today as a start.
Well, at the risk of being self-serving, you can find a close approximation to this lecture on the web, and I can also I'd be happy to send you the reference, and also, I wrote a paper, it's a little bit more technical, but it's on the subjects that I talked about here. I'd be happy to send that to you if you have an email, so I'll be happy to do that.
Okay, I think one last question.
At the risk of making a useless question, but people have joined quantum mechanics and philosophy, so let's join quantum mechanics and ethics. So suppose someday somebody figures out a way to really factorize prime numbers on the industrial scale. What's the ethical thing to do? Publish it so that everybody can break everybody's encryption? Don't publish it? Or tell it just to the right people?
Well, yeah. No, I mean, it's a good question. I think, one thing, this will be a little bit of a cop-out, but I think, since this has surfaced, certainly the intelligence community knows that this is going to be, extremely hard technology to build up to do useful factoring. And I think even though they want to keep secrets for 50 years, roughly, I don't think there's any need to worry for those guys, because the factoring problem is just so hard. So, I'd be surprised if there's one that could factorize big numbers in 50 years. So they'll make the right moves. If someone had a factoring machine tomorrow, then the NSA and people like that they wouldn't use public key encryption, and they do something else. So, I don't think I can avert the moral question a little bit. That I think it's just not practical to think about a useful device in a long time. So.
Okay, let's thank Professor Wineland again.